There we go, just a little more Trans-Siberian Orchestra to get you in the holiday mood here today. Nice intensity and upbeat, getting us fired up and ready to go and finish off the ratio test. I'll tell you what, our toolbox is just about stuffed full. We've got a whole bunch of series and tests in there, and biggest thing now is just trying to keep them all separate in our mind and getting ready to apply them when they're all mixed up. I think each one individually is a pretty manageable test. I think it makes sense, and now we just got to mix them all up and challenge ourselves that way. So first thing we're going to do is we're going to move on here. We're going to recap what the ratio test says, and then we'll start mixing them up. So hopefully you can go ahead and pretty much reiterate what our theorem said yesterday. There was those three possible outcomes, and it was all based on what this limit turned out to be. So here's what we're going to do just to shorten things up a little bit. We're going to say that the limit of the n plus first term compared to the nth term, let's say that equals L. Okay, we're going to let that carry through. So basically, if L turns out to be smaller than 1, that's a good thing. We said that the series converges. If L turns out to be greater than 1, that's a bad thing. That means the series diverges. And if L turns out to be equal to 1, then we say, well, inconclusive. Let's go back to the drawing board and pick a different test, shall we? So here are 7 examples. I hope you could read these. Did the best I could here with this goofy pen. Anyway, I want you to take some time, 5 to 8 minutes, or a little more if you're up for the challenge here, and try to use all the different series that we've looked at. I think, if I counted right, we've got approximately 8 series in our toolbox, so you may not use every single one. But I'd like to challenge you to try to use a different type of test on all 7 of these, and then come on back. I'm going to solve them one at a time and see if we got the same answers. Our first example is our absolute favorite test in the whole wide world, and I'm going to use the nth term test here. What you'll notice is the limit as n approaches infinity for this particular nth term. I've got same over same, ratio is 1/4. That's not equal to 0, so this baby has no prayer of converging. It's an instant diverge. So there's our favorite test right there. Our second one was a little more interesting. I went ahead and I used a comparison. Whoops, I don't want to give my inequality sign away too early here. I compared it to 1/4 to the times n. All we did is we stripped away that plus 1 we had right there. And basically what's happening is the series on the left has the bigger denominator, therefore the series on the right as a fraction as a whole is bigger. The other thing you can do with this series is you could pull out the 1/4. Okay, that's your coefficient. So then it's just 1 over n. Now you've got the harmonic. We refer to him by name. It's a special kind of P series, and that bear definitely diverges. Do we have anything conclusive at this moment right now yet? Well, I would say what we just proved. What did we just prove here? We just proved that the bigger one diverges. Does that tell us anything about the smaller series? No, inconclusive. So what I'm going to do here is I'm going to go back to the drawing board, so to speak, and I'm going to say, you know what if I compared this to 3n? Now, the 3n is very interesting. Did that help me at all? Well, I think I still have the bigger denominator on the left side, therefore making the fraction on the right bigger, and that didn't get us anywhere. So let's make one last attempt here to see if we could straighten this bear out. What if we compared it to 1/5n? Okay. Now I've got the bigger denominator on the right side. So that means I'm going to flip this inequality around. We could say now this is my bigger series over here. This is my smaller series. Similarly speaking, we could pull out the 1/5. It's getting a little messy. Hopefully you're still able to read this. Now we've got a harmonic. It's diverging. And we just proved, hey, if the smaller one diverges, guess what? Then this bigger one also diverges. So just be careful and make sure you don't fall into one of those inconclusive bear traps, and that we do get a divergent answer here. Number 3 jumped out at me right away as being a geometric series. We had a constant in the form of pi over 4 being raised to the nth power. So we knew right away that our common ratio is pi over 4. And because that's smaller than 1, we definitely have a convergent geometric series. And if they wanted me to, I could then go forward and use this cute little formula to find the actual sum. And of course, it wouldn't be the cleanest answer, but it'd be in terms of pi. Nonetheless, it would represent the sum of that series. This one I didn't think was quite as obvious, but I did end up jumping on the integral test. I noticed if I rewrote this as x e to the negative x squared and I sprinkle in my own dx, we could we're going to not only rewrite this in terms of a limit because it's an improper integral, but we're also going to jump right on our u sub here. We're going to let u equal the exponent, which is traditionally our first attempt on when we're integrating the e function. And we're going to end up solving for dx. We get something like this. So we've got the limit as b approaches infinity, integral from 1 to b. We've got our x, we've got our e to the u, and we've got our du divided by negative 2x. All right, good news. We kill the x's. We'll pull out the negative 1/2. Limit as b approaches infinity. We're going to slide the negative 1/2 way out there. And we've got the antiderivative of e to the u is e to the u, so we end up with negative x squared substituted in there. Bounds is 1 to b. Now, remember, the only thing we're really worried about here is let me make this point. We may not have to clean this up as much as you think. We just want to get to a point where we're convinced that this is either divergent or convergent. And because e was being raised to the negative b squared power, I'm going to put it on the bottom. And then we got 1 over e to the first power. And here's the key. As soon as you get to a point, you say, wait a minute, as b gets bigger, that term is approaching 0. And then, of course, this one over here is finite, of course, but it's really this term you want. As long as you get a finite number right there on that term, boom, we can say that that integral converges. And, of course, if the integral converges, the series also converges, although be it to a different value. I thought 5 was a dead giveaway. As soon as you saw this negative 1 to the nth power right there, that told you instantly that this is going to be an alternating series, and we're going to use the alternating series test. So condition number 1 says, what's the limit as n approaches infinity? For this component, we're not worried about the negative 1 part right now. And I ended up getting small over large, that's equal to 0. Which, because it's an alternating series, that's a good thing. Condition number 2 also says the n plus first term has to be smaller than or equal to the nth term. We could confirm that just by looking at the nth term, that they are getting smaller and smaller as n gets bigger. And therefore, because these two conditions are met, we're going to say we have a convergent alternating series. Now, when we're looking at example number 6 and you're debating about which test to use, two things jumped out at me. Number 1, I saw some factorials, and number 2, I saw an exponential function in there. So either one of those is a good tip that I'm going to go ahead and I'm going to use the ratio test that we just studied last night for the first time. A little bit more work involved, but we're going to say, okay, limit as n approaches infinity. Now I'm going to do the n plus first term. Basically all I'm doing is I'm substituting an n plus 1 in for every single n, which my numerator is actually going to become n times 6 to the n plus first power all over n plus 1 factorial. Now I'm going to multiply by the reciprocal of the given nth term, the one that's sitting right in front of me here. And now it's just time to start cleaning things up. This is the fun part right here. Let's see. Kill that bear, kill that bear. We got 6 to the first. We can kill that bear, and we strictly have n plus 1. Now, here's what do we have left? We got to sort through the rubbish here. We can pull out the 6, get him out of the way. Don't lose him. You're going to need him at some point. And let's see, we got an n there, and then we got an n plus 1 times an n minus 1 on the bottom. Okay, here's the deal. What kind of power fight do we have inside there? Okay, just focus on the limit for now. Don't worry about the 6. We've got small over large. We got first degree over second degree, so that limit has a value of 0. Then when you multiply by the 6, you strictly get 0. It's smaller than 1. Therefore, according to the ratio test, this bear is going to converge. Hopefully you were able to read the 7th problem here. If you can, I apologize, but it said the cubed root of n squared. Let's just rewrite that as a fractional exponent. We could pull the 4 out here if we wanted to, n to the 2/3 power. Visualize the great wall of divergence. Okay, here's what 1 over to the n looks like. Our series, because that exponent's smaller than 1, they're going to intersect at 1, 1, but then it's going to cut above. And so I'm going to say, because that p-value is smaller than or equal to 1, this p-series is going to diverge. Well, hopefully you did good on those 7 examples. Hopefully you're able to sort them out and keep all the tests straight. I wanted to do one more example here tonight about, just kind of has one special little condition in it. Just a real simple series here. We'll say it starts at 1 and ends at infinity. And we're going to go ahead and use the ratio test because we see that factorial sign. So we're going to set it up. Limit as n approaches infinity. Numerator is now n plus 1. And here's where I want you to be careful. Here's where I want to slow down just a little bit. Now remember, we're substituting an n plus 1 in for just the n right now. So really what we have here is it's by the time I substitute and distribute the 2, it's going to be 2n plus 2 factorial. And I can't stress this enough. We need to have a plus 2 right there. And again, you're substituting the n plus 1 in for n, and then you're distributing that 2, thus getting 2n plus 2. That's huge. Now we're just going to multiply by the reciprocal of the nth term. Okay, simple enough, right? Well, let's talk about how we're going to expand this factorial we see here on the bottom. It would be 2n plus 2 times the next smaller number. Notice I just subtracted 1 times the next smaller number, so on, so on, and so on. So I could put dot, 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 or I could just throw the factorial on there. I prefer to throw the factorial on there. Now what we could cancel, this bear can cancel that bear. Unfortunately, that's all that canceled, so it was a little bit disappointing there. But let's see what we got. We got an n plus 1 on top, and then I've got a 2n plus 2, I've got a 2n plus 1, and I've still got an n on the bottom. If we disregard all the terms except for the biggest terms, we're going to end up with an n on top, and it looks like a 4n cubed on the bottom. Definitely small over large, therefore the limit has a value of 0. And if the limit equals 0, that's certainly less than 1, and we have a very convergent series according to the ratio test. And I'll tell you what, I bet you took one look at this series when I first put it on the screen. I bet you were screaming convergent right from the get-go. It was just a matter of proving it. And if you take away anything from this problem, I want you to really make sure we get that 2n plus 2 right there instead of 2n plus 1. Well, that's going to do it for our what I call our simple series. And you're probably wondering, what's the big deal? We put a lot of hype into this chapter as we started. You know, you're thinking right now, series weren't that hard. What's the big deal? I thought this was supposed to be Mount Everest, etc., etc., etc. Well, I'll tell you what. We're just building up, I should say. We're at the foot of the mountain still. We are building up for something called a power series, okay? And we needed to really understand the ins and outs of very simple series like the ones we've been doing before we can graduate to what's called a power series. And that's what we'll be ready to do when we come back after break, okay? And a power series is basically a series that is in terms of x. Okay, so it's going to, here's the general form, and it's an infinite series, not a finite, but an infinite series. So when I start, you'll notice what's new is we didn't used to have that part. That's what's new now that we talk about a power series. So as I start to substitute, if I substituted, in fact, you know what, I'm going to start this one at 0. If I substitute a 0, I just get 1. Okay, a sub 0 times 1, I should say, plus a sub 1 times x to the first, plus a sub 2 times x squared, yada, yada, yada. Then we would get plus a sub n times x to the n plus dot, dot, dot to show that it goes on forever and ever. And what you'll notice is we are creating a polynomial here. Okay, what we're creating is a polynomial that's in terms of x. It's a polynomial because, like we said, it's x to the first, x squared, x cubed, x to the fourth, etc., etc. It's a very well-behaved polynomial. Polynomials are great to work with. They're guaranteed to be continuous. They're just awesome functions to work with. And eventually what we're going to do is we're going to create polynomials that we use to replicate trig functions, exponential functions, logarithmic functions, etc., etc. And again, what's the big deal? Why would I want to use a polynomial function to represent and mimic a trig function? Well, guess what? When you start taking multiple derivatives, and I mean way beyond second derivative. I'm talking about 7th derivative, 8th derivative, 20th derivative. It's a lot easier to take the derivative of a polynomial than some of these other crazy functions that we might see. So we'll continue to get into the advantages of them, but I just want to paint a picture of where we're going and why we're going there so that you can kind of appreciate why we had to spend all this time on some basic series over the past 2 weeks and learning all these crazy tests. So hopefully it's coming together. Hopefully your confidence is building, and we've got a nice test coming up soon.